I am representing Vs in terms of the other three scales here, velocity and the length scale. So with this I can apply the scales to the u momentum equation. Okay, so let's go and do this. So we'll take equation 2 now. Equation 2, that is your u bar equation, u momentum equation. Okay, let me just copy it. So I have the equation ready here, which is my u momentum equation, right? So I would now start to introduce the scales. Okay, so introducing the scales. So for u bar I have us, this is delta us by L, and for the next one v bar it's vs, right? So that is vs delta us by delta. Okay, and for the p bar we didn't do anything, right? I intentionally did not do anything there. I'll tell you why. So I have not introduced a scale here. I'm going to keep it as a question mark here. This does not mean that this term is not important. Okay, it is certainly an important term, but we would like to keep it as a question mark. I'll reveal why I don't want to take this into the game now. So let's look at the other scales here. So I have this new dou square u bar. So change all changes, I have the same scale here, delta us by dou x. This is dou x by, basically it's not the square term here, right? So it is the way it's written. I have written like this, it's dou x, dou y and so on. So this will be L square, new delta us by L square, and this will be new delta us by delta square. Simply introducing the scales. And for the turbulent quantity, this is u square, a single turbulence velocity scale, u square by L, and this is u square by delta. I told you URMS is of the same order of magnitude as VRMS, and therefore both the normal stress and the shear stress, the Reynolds stresses, I am using V square. That is the argument I already placed. So now if I look into the LHS and the RHS here, right? So this is the left hand side part, okay, and the right hand side part. So which is the largest left hand side term here? That will reveal if I go into substitute Vs here. Okay, so if I substitute the Vs value, which is delta us delta by L, delta us by delta. So essentially this cancelling out. So if I compare between the two terms here, this is us delta us by L, right, and this is delta us by L. Okay, I rewrite this as like this. So you see this is, so which is the smallest term on the left hand side? The first term, oh sorry, the largest term I am talking about. The second term is the smallest one. So which is the largest term? Obviously us is an order of magnitude, this particular term is an order of magnitude larger than delta us, right? So this is the largest term on the left hand side. This is the largest LHS term, the first term. So because of this, I would like to know which term will balance this particular term. Is this clear? Why the first term is the largest left hand side term? Because us is an order of magnitude larger than delta us. Okay, so let's divide throughout by the largest LHS term. So divide throughout by largest LHS term to see which term balances this in the entire equation. So if I do this, here I will get as this becomes 1. Okay, so this if I divide, so I get delta US by L divided by US delta US by L. So obviously this is going out, giving me only delta US by S term. Okay, this I have retained as it is, this pressure. I have not done anything with that. I have not introduced a scale there. So now we have the other term, which is nu delta US by L 1 by L, okay, divided by, I have US delta US by L. So this and this cancels out, giving me this, and then I have the next one, which is nu delta US by delta 1 by delta over US delta US by L. So here only the delta US term goes away, leaving out this, and then I have the two Reynolds stress terms, which is I have this U square by L by US delta US by L. So the L term goes away. I have U square by delta over US delta US by L. Here no term goes away here, every term is retained. So now if I rearrange, what do I get? If I rearrange here, I can write this as, so this is essentially 1 as before. I have here delta US by S, sorry, delta US by US, this is a question mark. The second term on the left hand side, we already know that this cannot balance the first term because it's already an order of magnitude smaller. So this term cannot balance anything on this. So the sum term on the right hand side must only balance this particular term. So sum term on the right hand side must be of the order of magnitude 1 to balance this. So which one is that? We have to choose. We have option between 4 terms. First we will see which is the largest viscous term, which is the largest turbulence term. Okay, so now we have the two viscous terms here. So which is, if I rewrite this, I will get essentially, this is nu by USL. Okay, and what does this look like? Reynolds number, right? So I can write this as essentially 1 over your REL. So this is nothing but 1 by REL, and this particular term, similarly I have nu by, let's say, US delta, and I have the other term which is L by delta here. Okay, so if I write this, I would get 1 by RE delta L by delta, right? 1 by RE delta L by delta. Okay, so now which is the largest viscous term here? The second one. See, the REL So we said L is at least an order of magnitude larger than delta, right? So 1 by REL must be then smaller than 1 by RE delta. Let's say REL is 10 raised to 6, 1 million, then 1 by RE delta, or the RE delta will be at least 10 power of 5, right? At least. So this will be a larger term, because L by delta is at least 10, the ratio is at least 10, it can be 100 or more. So this will be the largest viscous term here, but still if REL is very large, this term should be negligible. So we will see the other two terms before I come to this. We have this turbulence term, which is U square by US delta US, and then you have same U square by US delta US L by delta. Okay, so I have the term in between these two, which is larger, obviously the last term. So this last term is nothing but this one. If you see, it's dou by dou y. In a boundary layer, the wall normal gradient of your Reynolds shear stress, dou by dou y part is becoming larger than the dou by dou x term. So this is the largest turbulent term here, because L is at least an order of magnitude larger than delta. So this is the largest turbulence term. Okay, because L is at least an order of magnitude larger than delta. Okay, if delta is 10, L is 100 minimum. That's the consideration we have. So the largest turbulence term is identified. So now there is a competition between the largest turbulence term and the other two viscous terms. Obviously 1 by REL cannot compete here for large Reynolds numbers. Okay, if I have Reynolds numbers being very large, so for let's say REL is very large, okay, high Reynolds numbers, this term becomes negligible. Okay, for high Reynolds numbers. What about this term? This is RE delta. This particular term, if REL is very large, then this term also can be small. Okay, but if RE delta is not that large, that means if you have low Reynolds numbers, then you can retain this term. But for very high Reynolds numbers, it is still small. For example, if I take REL to be 10 raised to 6, as I said, 1 million Reynolds number, and considering that L and delta is one order of magnitude different, then RE delta will be 10 raised to 5, okay, and L by delta is 10, so this will give me 1 by 10 raised to 4, which is still small. Okay, so this will be still small for large RE delta. So that means there is no other competition here now. The largest turbulence term must be balancing the left hand side term here. Okay, of course, unless we want the pressure term to participate. So now we have the largest turbulence term, so therefore I can say, here I can say here it's also negligible. Therefore the largest turbulence term must be balancing the LHS or the largest LHS term. So this is, we are looking at first order. This does not mean that the other terms are all negligible and dropped. They are of second order, third order importance. One can also find which is the second order important term, and that is being balanced by the other term. To first order, we are looking into what are the two terms that are balancing each other, right? So this is to first order we are looking at. To first order. So what is now we have learned is that this particular thing implies that 1 is of the same order of magnitude as u square by us delta us L by delta, which is nothing but delta by L is of the same order of magnitude as u square by us delta us. Okay. So to first order we have an expression here in the equation. Delta by L is of the same order of magnitude as u square by us delta us. Of course we have not let the pressure participate here. I'll tell you why. But in this, is there something to learn from this equation? Delta by L is of the same order of magnitude as u square by us delta us. What is delta by L? The growth of boundary layer. The boundary layer growth. What is it depending on now? Sorry? Velocity, turbulence velocity. Something like a non-dimensionalized turbulence velocity. This we call it turbulence intensity. Right? So we have, let's say u, the small u is, let's say 1 meters per second, and us delta us is, we are using it to non-dimensionalize it. Or let's say in a flow you have 10 meters per second is as your the inflow velocity, and the turbulence velocity, let's say, is 1 meters per second. Then you can say the small u by capital U is 0.1. So you can say 10% turbulence intensity, you know, a rough value. How much turbulence, somebody can ask you how much turbulence you have, you can say okay, 10% turbulence. So this is essentially what this means is, I have this delta is the boundary layer growth. Boundary layer growth is of the same order of magnitude as turbulence intensity, a non-dimensional turbulence velocity. So as turbulence intensity increases, your boundary layer is growing. So something we learned, that what is the turbulent boundary layer is depending on. You may know about a laminar boundary layer growth, delta. What does that depend on? But in a turbulent boundary layer, maybe we at least know without doing any experiment or simulation that to first order, the boundary layer grows based on turbulence intensity. Higher the turbulence intensity, higher the turbulent boundary layer growth. Of course, with the considerations that we had, we took a flow where there is no boundary layer separation. That means some of the terms may pop in if you have those things, right? We have considered a thin boundary layer and all these things. This is what we have got. And we have another consideration here, the pressure term that we have not taken into consideration. Okay, so I'll continue in the next class why this pressure term is not being considered. Okay.